how can we model the fact that the source is not point light, or the propagation medium is not ideal, and it introduces some decorrelation between the sensor, so spatially decorrelation. So how can we change this ideal model that we derive? There are different approaches that are similar. So I will say something about this, okay? But I mean, what is important to understand is that first, you have to understand the simplified model and what are the assumptions that have been made at the beginning to derive the simplified model. Then we say, okay, some of the initial assumptions are not valid. And the question is, how should we modify the simplified model to come up with a model that is more realistic? But we start from the simplified model to find a more realistic model. So what we have described so far is very important also to understand more realistic models, okay? Now, if the source is spread, so is distributed over a space, or the medium is not ideal, how can we complicate, how can we change the previous model, the previous ideal model, to take this non-ideal effect into account? The most commonly adopted model is the following. We assume that the steering vector, instead of being deterministic, is random and time varying. So it becomes a time varying random vector. So it can change with time in a random manner. Okay. So when you make an experiment, so you collect your n snapshot, what you observe is a particular realization of the random vector v. So you have to understand this. And obviously, we want to solve the problem based on the observation of that particular realization. What is the covariance matrix? Now, because we rely on second-order statistics, what is the covariance matrix in this case? So we calculate, as usual, the expectation of y Hermitian. And obviously, the noise part is the same as before. What changes is the signal. So instead of A Hermitian, we have the expectation of V Hermitian. Now, what we assume typically is that the covariance matrix of the random steering vector V does not depend on time, does not change with time. And so you get something like this. So what happens is that now it is no more true that the rank of the signal covariance matrix is equal to the number of targets. So if you have just one target, it's no more true that this matrix is rank 1. But typically, this becomes a full rank matrix. Now, what is the model most widely assumed for the spatial correlation matrix is the following. A Hermitian is the correlation matrix that we would have in the ideal condition, so if you have a point-like target coming from angle theta, and we have only one. Now, if the source of signal is distributed in angle, so if the generated power is not concentrated in a particular angle, but comes from, let's say, a sector, and we need to know how the generated power is distributed in angle, and then we can get the overall correlation matrix basically by averaging the rank 1 matrix over theta. So you sum, I mean, you can read this integral as a sum. So you sum all the contribution from different angles. If the source is continuously distributed in angle, instead of a sum, you have an integral. So, I mean, this is called normalized angular power density, but it's a sort of probability density function. But instead of describing the distribution of the probability, it describes the distribution of the power in angle. So instead of having a point-like target, you have a target or a source that is made by a cluster of scatterers distributed over a sector omega. And so P of theta is a function that describes how the power generated changes as a function of the directional arrival theta. Now, if the scatterer are all contained in the sector theta, the area of this distribution over the sector theta should be normalized equal to 1. So it's a normalized distribution of the power. Clearly, if you have a point-like target and the direction arrival is theta 0, P of theta is what? Is a Dirac delta function of theta minus theta 0, obviously. So the point-like target case is a particular case of this representation when this distribution is a Dirac delta function centered at the unique angle of arrival of the signal. Now, the problem is that we never know P of theta. And a typical approach is to use a parametric model. And the typical approach is to assume that P of theta has a Gaussian shape, so normal shape. Now, you know that any normal or Gaussian model is fully characterized by two parameters. One is the mean, the other is the variance. In this case, the mean is the barycenter of the distribution of scatterers. And so the barycenter can be interpreted as the directional arrival of the signal generated by this bunch of scatterers. And sigma theta square is a measure of spread of the source. So it measures how much the source is spread in space, or actually in angle in this case. So if you make this replacement in the previous equation, basically we have that the covariance matrix of the signal of interest depends on parametrically on two parameters, because it is the solution of this integral. And these two parameters are the barycenter of the scatterers that constitutes the source, And the other parameter is a measure of dispersion of the scatterers around the barycenter. And as I said before, the point-like source model is a particular case that is obtained if you replace the Gaussian with the Dirac delta function. So if you make this replacement, the dispersion is zero because all the power comes from direction theta t, and this direction is also the barycenter. And so in this case, the only parameter you want to estimate is theta t, and the rank of the matrix is equal to 1. So if you have one point-like source, the covariance matrix is as rank 1. If the source is spreaded, the covariance matrix is full rank. It depends on an additional parameter, sigma theta square, and this parameter measures the spread of scatterers around the barycenter. And when we solve the estimation problem, we want to estimate the barycenter and the spread of the source. There are various methods. A typical method to estimate these two parameters is to use a method that is called covariance matching estimation technique, COMET. And basically, it's a method that it is inspired by the well-known linear least square method. So in the linear least square method, you minimize the distance. So the least square method, you minimize the distance between the data and the parametric model of the data. COMET basically rely on the same idea, but instead of the data, you have an estimate of the covariance matrix obtained from the data minus the parametric model. And the parametric model, if the disturbance is wide, depends on 4 parameters that are the power of the source, the barycenter of the source, the spread of the source, and the disturbance power. And so then you calculate the Frobenius norm of the difference, and an estimate of the unknown parameters is obtained by minimizing the distance between the sample covariance matrix and the parametric model. So this is one possible method to estimate the unknown parameters, including the direction arrival, theta t, if instead of point-like sources, we have spread sources. Another method is basically to use a beamformer. You will see later in the course what is a beamformer. We'll investigate classical beamformer, K-home beamformer, other adaptive beamformer. So use one of the beamformer that you will see in the next days to estimate the distribution of the power in angle, and this is called source angular power density. So we estimate this function by using a beamformer, and then we calculate the barycenter and the dispersion of this distribution by using the definition of barycenter and dispersion. And I mean, this is more simple than this other from a computational point of view, so it's a different method. To close this part, another quite important special case where spread model applies is shows up typically in radar imaging. So synthetic aperture radar, radar interferometry, and so on. And basically, in this application, we model the decorrelation introduced by the fact that the sources are not point-like but are distributed. We model by representing the random steering vector V as the Sure product. Sure product is the element-wise multiplication. So the first element by the first element, the second element by the second element. So basically, we modify the ideal model by multiplying by this random vector G. And in other words, we introduce in the model multiplicative noise. So W is additive noise. G is multiplicative noise. And in radar imaging, this multiplicative noise sometimes is called speckle. So the speckle is multiplicative noise. And you take into account, and the effect is a decorrelation of the spatial samples. And so it's slightly different than the previous modeling of W. So I repeat, we introduce the concept of multiplicative noise, and we assume that the correlation effect, due to the fact that the source is distributed or the medium is dispersive, we model this effect by introducing multiplicative noise. And the steering vector is the Sure product between multiplicative noise and the ideal steering vector. Now, what is the correlation matrix in this case? You calculate the correlation matrix by using the definition. Then you use the property of the Sure product. And the nice thing is that at the end, the covariance matrix, the spatial covariance matrix of the array output is the spatial covariance matrix of the speckle of the multiplicative noise that multiplies point by point, element by element, the ideal correlation matrix. And if you have only one target, the rank is 1. After you have multiplied by the noise, obviously, the rank is no more equal to the number of targets, the number of sources. So this is the effect. So you model the effect, the fact that the source is spread and not point-like, by introducing multiplicative noise. And the presence of multiplicative noise in the array correlation matrix is represented by this term here. Now, again, this matrix is called coherence loss matrix because coherence loss is equivalent to, say, correlation loss or decorrelation. So this matrix has a shape that takes into account of the decorrelation effect that we have. And a typical approach is to introduce a parametric model of this matrix. And one possibility, I mean, these are two commonly used parametric models for the coherence loss matrix. In the first case, it assumed that the correlation decrease exponentially, and the speed of decrease, so how fast the signal decorrelates from one sensor to the other, is controlled by this parameter mu that is called coherence loss parameter. Another model is the Gaussian one, this one, so you have the square. Another model for decorrelation using radar interferometry is the linear one, where the decrease is linear, so like a triangle. In any case, I repeat, in the presence of multiplicative noise, so if the point source assumption is not valid and you have to introduce multiplicative noise in the model, what happens is that the rank of the signal matrix is no more equal to the number of targets. I think, no, I mean, I stop here about the I mean, about the spread, the model for spread sources. And now we talk about beam pattern and beam forming. So I ask. So I go to the second chapter. I sent to Professor Badri the first two chapters. I will send soon also all the other chapters and also the MATLAB code that I have used to derive the numerical results. But you will see this, I mean, you will receive this later. So in other words, what I wanted to show at the end of previous chapter is that we derive a model under simplifying assumption. But this result is very important. First of all, because many algorithms have been derived by using this simplified model. Secondly, because if some of the assumption cannot be assumed to be valid, starting from the simplified model, you can complicate the model. Starting from that model, you can complicate the model to take more realistic assumption into account properly. But it's fundamental that you understand the simplified model and under what assumption it has been derived. Because only in that case you can be able to understand how that model should be modified to make it accurate in a more realistic scenario. Okay. Can I continue? Are you still there? Because it's
Yes,
quite
sir.
thank you.
Yes, sir. Yes, sir. We can continue till 5.
Okay. Actually, if you have questions, you can also send me an email later. And if it is not difficult, I can answer by mail or I can answer maybe in the next days. So you find here my email address. So I repeat, you can send me emails if you want. Okay, now let's introduce the concept of beam pattern and let's derive the classical beamformer. Now, the term beamforming is synonymous of spatial filtering. I mean, if we have only one sensor, we collect samples in time, and we can apply a linear filter. So we do temporal linear filtering to achieve some purpose. Now, you have studied Fourier analysis, signal and system, I guess. What is the purpose of performing a temporal linear filtering? The purpose is the following. Okay, the purpose is the following. You use a linear filter to enhance, to amplify the frequency component where the signal of interest dominates on the noise, and you try to attenuate as much as possible the frequency components where the noise dominates on the signal. So if your signal is a passband signal, for example, with central frequency around 10 kilohertz, the filtering that you typically perform on the signal is a bandpass filter with central frequency around 10 kilohertz. So you try to, not to attenuate or to amplify the frequency component where the signal dominates, and where the signal is negligible and there is only noise, you try to attenuate as much as possible. So in this way, you try to eliminate the noise components outside the bandwidth of the signal. This is the purpose of temporal linear filtering. Now, if you sample the signal in space, so you observe the signal in different locations, so you implement an array, so you observe one snapshot. So one snapshot is a spatial vector. If we do a linear filtering of this spatial vector, so spatial linear filtering, what is the goal that we want to achieve? Well, you will see that the idea is very similar, but now instead of the frequency, the domain is the angle of arrival. So we want to achieve a similar goal. So we want to discriminate signal and noise, but not based on the frequency content of the signal, but based on the direction arrival. But the things are very similar. So if you understand temporal linear filtering, you understand spatial linear filtering, that is called beamforming. Now, to make this analogy 100% clear, let's go back to the temporal filtering in the time domain. So let's assume that we have our input data, x of n, so n is the time. We filter x with an FIR filter, linear time invariant FIR. FIR is the acronym for finite impulse response. So the output is the linear convolution between the input signal x and the impulse response of the filter h. If the filter is FIR, the summation goes from 0 to m minus 1. If m is the number of non-zero value of the impulse response. Now, this linear convolution can be expressed in compact notation by using vector notation. So you define this row vector m-dimensional. Remember, m in this case is the number, m is the number of samples. So we call this H-Hermitian. So we define this row vector. And the linear convolution can be expressed as H-Hermitian that multiplies this column vector. So when I goes from 0 to m minus 1, here what you get is x of n minus 1, x of n minus 2, up to x of n minus m minus 1. So you can express in compact notation the output of the FIR filter at time n in this way, as H-Hermitian that multiplies x of n. So the length of the impulse response of the filter is m. So this is a sort of window of length m that run over your data. So at time n, to calculate the output, you use the sample at time n and the other previous m minus 1 samples, okay? So this is the output of the FIR filter. Now, you should remember that if the input is a complex exponential at frequency f, what is the output of a linear time invariant filter? So if this is the input, the vector x has this structure. So you have x of n minus 1, and so on. So you can express this vector x as e to j to pi f n, and then you have n minus 1, n minus 2, and so on. If you write all these terms and you bring outside e to j to pi f n, what remains in this vector is 1, e to minus j to pi f, e to minus j to pi to f, and so on, up to e minus j to pi f n minus 1. If you call this vector A, this is the input signal, you can see that X is the temporal steering vector. This is what is called temporal steering vector that multiplies the input signal. Okay, now if you plug this in the expression above, so if you calculate the output of the filter, H-Hermitian X, what you get is H-Hermitian A that multiplies x of n. X of n is a scalar, is the input. So if the input is a complex exponential, the output is proportional to the input. And this proportionality term is what? Is H-Hermitian A. Now, if you calculate explicitly H-Hermitian A, H-Hermitian A is the inner product between these two vectors. So it's the summation from 0 to n minus 1, h of n, e to minus j to pi f n. By definition, this is what? This is the frequency response of the filter calculated at the input frequency f. So in other words, if the input is a complex exponential, the output is the input scaled by a factor that is a complex factor, that is the frequency response of the filter calculated at the frequency of the input signal. So we typically say that complex exponential are eigenfunction of linear time invariant systems, and the associated eigenvalue is this term here. So it's the frequency response calculated at the frequency of the input signal. And from this result, you understand that we can design the filter h of n, or equivalently capital H, which is the frequency response. So we can design the frequency response in a way that it attenuates the frequency components where the signal of interest is weak, and it enhances the frequency component where the signal of interest is strong. So basically, we design the filter based on what we know about the frequency content of the signal of interest and the noise. And we try to eliminate, to attenuate as much as possible the noise. And in particular, by using linear time invariant filter, we can eliminate the noise in the bandwidth, in the frequency outside the bandwidth of the signal. These are basic concepts that you should have learned from signals and system course, okay? Now we have the signal in the spatial domain. Why? The question is, what can we gain from performing a spatial filtering? So the summation now is not over n, the time, but over m, which is the space. So if at a given time we implement a linear FIR filter of order m that works in the spatial domain, so the summation, I repeat, is over the spatial dimension m, what can we gain? So what is the benefit that we can achieve? Now, to understand this, let's write again the impulse response of the m-dimensional spatial FIR filter as a row vector, and we call it H Hermitian. Then we define the column vector, the m-dimensional column vector that contains the output at time n of each sensor from 1 to m. So this linear convolution can be expressed in this way, okay? Now, if we replace y with the narrow band model that we derived so far, assuming that there is only one source, and forget the noise. So if there is only one source, y, this expression here. Now, this is the array response. Now, let's assume for the time being that the array is a Euler array. In general, A depends on the geometry. But let's assume, to start with the simplest possible case, that the array is a uniform linear array. In that case, we have already calculated that the array response is given by this expression here, okay? Now, what is the output of the spatial linear filter, FIR filter, it is H Hermitian Y. So you replace Y with AS, and again, H Hermitian A is a complex scalar term that we call H of theta. Now it depends not on the frequency, but it depends on the angle of arrival, the direction of arrival. So it's equivalent of the frequency response, but now the value change depending on the direction of arrival. So in other words, by using temporal filtering, we can discriminate signal from noise based on their content in the frequency domain. This result tells you that we can design the spatial filter H in order to discriminate between signal and noise in the direction arrival domain, so based on their direction arrival. So we can build a spatial filter that has the ability to separate signal from disturbance based on their directional arrival. So spatial filtering allows to discriminate incoming signal based on their directional arrival. So spatial filtering basically introduces an additional degrees of freedom that allow to discriminate signal of interest from noise, not only based on the frequency content, but also based on the direction of arrival. So it's an extra degree of freedom that can be used to improve our ability to separate signal of interest from noise. Now, when you perform spatial frequency, this term here is the equivalent of the frequency response. But because the domain is the angle of arrival and not the frequency, we don't call this frequency response. It is the transfer function of the spatial filter. And because it describes the selectivity of the filter depending on the value of the direction of arrival, this quantity here is typically called beam pattern. So the array beam pattern in spatial filtering is the equivalent of the frequency response in temporal frequency. So this is a very important concept. Now, if the array is EULA, the array response is this complex exponential at the spatial frequency Fs, which is related to the direction of arrival. And so if the array is EULA, you see that the beam pattern is just the Fourier transform of the impulse response of the spatial filter. If the array is not EULA, okay, this inner product is no more the Fourier transform. It's no more the discrete time Fourier transform. Something else, whatever it is. You have to calculate this inner product and then you find the array beam pattern. But in the case of EULA, the beam pattern is the Fourier transform of the impulse response of the special field. Okay. For example, this is the beam pattern of, so the beam pattern is the modulo of this inner product. In general, it is complex value. So when you plot the modulo, and what you see is the polar representation of the beam pattern of a special filter in the case where the array is a EULA composed by 10 elements, and H, the H is choose to be equal to the array response calculated at theta equal 25 degrees. So if you select H in this way, what you obtain is that you build a digital beam pattern with the maximum at angle theta 0, 25 degrees. So in other words, this choice of the special frequency, special impulse response, you are creating a digital beam pointed at 25 degrees. So if you want to point the beam in other direction, you change the angle, you recalculate H, and then you implement the new filter. So in this way, by changing H, you can create different beam pattern pointing in different direction. So when you implement, for example, this beam pattern, what is the result? The result is basically that you allow to pass at the output of the special filter all the signal coming from 25 degrees, and then you attenuate through the side lobes all the signal coming from different angles. So you, in other words, you try to isolate as much as possible the signal coming from a specific direction. So through spatial filtering, we introduce selectivity in the angle domain. Instead, temporal processing is a way to implement selectivity in the frequency domain. But if you understand temporal processing and selectivity in the frequency domain, you should also understand that spatial processing allows to introduce selectivity in the angle domain. So it's an additional degree of freedom that allows you a better separation, not only in the frequency domain, but also in the angle domain, between signal of interest and disturbance. And the array beam pattern is the equivalent of the frequency response and tells you the behavior, how a signal is attenuated based on its directional around. So the problem that I want to address in the last 15 minutes is the following. If you have understood that by properly designing the FIR spatial filter H, so it's an FIR filter, why? Because the impulse response has exactly the same size as the number of received elements in the array. And the number of elements in the array is finite. So the spatial filter is always an FIR filter, always. So the problem is how to design the filter H in order to allow only the signal of interest coming from a specific direction to pass, and at the same time filtering out as much as possible all the disturbance, all the interferences coming from different angles. And I repeat, you may have interference that occupy the same frequency range as the signal of interest. In that case, you cannot separate signal from interference based on temporal processing. So you have to separate them in a different domain. So if they come from different angles, you can separate them through spatial processing. So through beamforming. Beamforming is synonymous of spatial processing. So how to design the filter? Now, let's assume that we want that a signal that comes from the angle theta passes undistorted, and we want to attenuate as much as possible all the signal coming from different angles. So we want basically to steer the beam in direction theta. And then obviously we can change theta in sequence. So we start from a value of theta, and then we change, and then we change, and then we change. So we span the entire sector of interest in sequence. So what is called filter bank approach to directional arrival estimation basically rely on 3 steps. So the first step is design the filter H in the way I told you before. The second step is sweep theta in the interval of angles of interest, so the OR range of interest, and calculate the power at the output of the filter. So we measure how much power comes from a given theta, how much power comes from another theta, and so on, for different values of theta. And the third, so basically we measure how the power is distributed in angle. The third step is look for the dominant peaks in this function, and the number of peaks is equal to the number of sources, and the values of theta for which we have the peak are the directional arrival of these sources. This is the idea. Now, what is the expression of the power of the output of the filter? So the output of the filter is this YF of n. YF of n is this one. So we have the nth snapshot. We calculate this inner product. So we calculate the output of the spatial filter at time n. This filter H, has a beam pattern that points at a given direction theta. We calculate for each theta the power of the output, and then we plot as a function of theta. How do we calculate the power of the output for a given theta? It is the expectation of the modulo square of the output. So it is the expectation of the modulo square of H median Y of n. Now the modulo square can be expressed in this way. H Hermitian Y that multiplies the Hermitian. So the Hermitian of this is what? Is Y Hermitian H. Okay, next step is bring outside the expectation what is deterministic. H Hermitian is deterministic, H is deterministic. So you bring outside, and so you get this. But what remains here is what? By definition, is the correlation covariance matrix of the array output, Y. And so Py of theta can be expressed in this way. And it depends on theta because by changing H, you change the pointing direction. So the dependency on theta is hidden in H. Now, we want to solve this problem. So how do we derive the classical beamformer? The classical beamformer, what is called classical beamformer, is derived relying at the design level on a simplifying assumption. So because we don't know Ry, let's assume at the design level that the covariant, this correlation matrix coincides with the identity matrix. So in other words, at the design level, we assume that the array output is partially white. So the values are uncorrelated. Obviously, if there is a source, this is not true. But we make this assumption only at the design level. Why we make this assumption? Because we don't know Ry, and we want to eliminate the dependency on Ry. So if you make this assumption, Py of theta becomes H Hermitian H. Okay. So the filter design problems becomes the following. Remember, step 1, step 2. We want that if there is a signal coming from direction theta, this signal passes undistorted through the filter. So H Hermitian A of theta should be equal to 1. So this is the constraint. So we want to impose the constraint that if there is a signal coming from angle theta, so the signal of interest in the vector y is proportional to this, the output of the filter, which is this one, is equal to 1. So this signal is not attenuated. So it passes undistorted. At the same time, we want to minimize the contribution from the other angles. And how do we minimize the contribution from the other angles? Minimizing the power at the output of the filter. And with the assumption that we have made, the power is expressed by H Hermitian H. So remember. So the assumption that Ry is equal to the identity matrix basically allows to eliminate the dependency on Ry in our optimization problem. Now that we have eliminated the dependency on the unknown Ry, we can solve the problem. Now, how do we solve this problem? I hope you are familiar with the Lagrange method, which is a method to solve an optimization problem with constraints. Now, we have one constraint, but because this constraint is complex, this quantity are complex value, the constraint is written in this way. So you have lambda 1 minus A Hermitian H plus the complex conjugate. So the Hermitian of the first term. So we have a constraint on first constraint that is the classical one plus the Hermitian. This problem can be solved by calculating the gradient. So you calculate the gradient. The gradient is you obtain H conjugated minus lambda A conjugated. You can write in this way. You put the conjugate in evidence and you find the optimal solution by setting the gradient equal to 0. And the solution is H equal lambda conjugate times A. So the optimal filter is a matched filter because it's proportional to the incoming signal vector, which is A multiplied by S of n. Now, how do we find lambda, the Lagrange multiplier? We find lambda by imposing that the constraint is satisfied. So this is the constraint. You replace H with this, and you find that lambda should make the constraint valid. And so lambda is 1 divided by H Hermitian A. A Hermitian A basically is the energy of A by definition, is the modulo 2, no, is the Euclidean norm square of vector A. So in other words, it's the energy of A, the sum of all the elements modulo square. And so this is the solution of the optimization problem obtained by relying on this assumption that Ry is equal to the identity matrix. And the solution, this is a constant term, the solution is proportional to the array response. And so in other words, is a matched filter. So for example, if the array is Euler, the energy of the array response is the energy squared. So the energy is 1 plus 1 plus 1 m times, so is m. So if the array is Euler, the solution of the optimization is this one. And so in other words, what is called classical beamformer is nothing but a matched filter, but matched in the spatial domain. So it's proportional to the spatial steering vector. So it's proportional to the received signal at the output of the array in the spatial domain. And you can calculate the output of the classical beamformer. So you go back to the previous expression, this one, you replace HB with this, and you find the output, the power and the output of the classical beamformer. Obviously, A depends on theta. If you want to calculate not only the power, but the spatial power spectral density, so the density of power, basically you have to divide by the bandwidth of the filter. Now, the filter is an FIR filter of length m. Roughly speaking, the bandwidth is the reciprocal of the length, 1 over m. And so you multiply this by m, and what you get is this one. So this expression, which is a function of theta, because A depends on theta, so the filter depends on theta, A depends on theta. So this is the spatial power spectral density obtained by using the classical beamformer. Just 1 minute, and then I conclude. Obviously, we don't know Ry, and so what we do clearly is we replace Ry with an estimate. Which estimate? We use typically the sample covariance matrix. So because we don't know Ry, we replace the expectation with the arithmetic mean, and so we plug R hat in this expression. So we start from this. We replace Ry with R hat with the sample covariance matrix. You make the replacement, and you find the spatial power spectral density estimate by using the classical beamformer. So you take your snapshot, you calculate the inner product with A, so you pass through a spatial filter with impulse response A, then you take the modulo square of the output and you average over all the temporal snapshot. So for n that goes from 0 to n minus 1. So you can express this spatial power spectral density estimate in this way, or in this way. Now, if the array is Euler, to calculate this inner product is equivalent to calculate the Fourier transform. So this is the Fourier transform modulo square divided by m. So we take one snapshot, we calculate the Fourier transform modulo square and divide by the size. And this is something well known. This is called periodogram. So for each snapshot, you calculate the periodogram, and then you average over time. So you average with respect to different snapshots. So in other words, the spatial power spectral density estimate that you obtain by using the classical beamformer, which is a spatial filter with the impulse response reported here, is nothing but the average periodogram. So you calculate the periodogram for each snapshot, and then you average over different snapshots. Okay, I think we should stop here and we should continue tomorrow.
Yes, sir. Thank you, sir. Thank you for today's session.
Any question from audience? If anyone want to ask any question, please open to ask.
Yes. You can check the view graph and you can send me question by mail later, and I can try to answer either by mail or tomorrow when we start the second day tomorrow. If you want to think before asking. But if you have question, please ask. No worry.
Hello.
Yeah, you can continue. Please ask.
Actually, can we use this direction of arrival techniques for satellite based tracking?
Yeah, obviously. Yes,
Okay.
absolutely, yes.
If
Okay.
there any question you may ask.
Sorry? Can you repeat? Sorry.
No, I'm asking if anyone else have any question, they can ask now. Otherwise, we can close the session.
Okay, tomorrow I start again from here.
Yeah.
Okay, sir.
Okay then. Oh, I think that is fine. We can close the session for today.
Okay, sir. We will close the session now. Thank you all.
Bye. See you tomorrow.
See you tomorrow. Thank you.
Okay.
Thank you, sir.